Hi class, welcome to the next section, the last section for chapter 3. Today is 3.3, the derivative as a function. So we talked about the limit definition of a function. We talked about some of the applications of the derivative, looking at it in terms of instantaneous velocity. We talked about how it's the slope of the tangent line, certain little things. So today we're going to just kind of flesh that out a little bit more. We're going to look at the derivative as a function. Okay, so the derivative is more so than just the instantaneous rate of change at a specific point. We also have a derivative function. So we'll talk about how to find that and how to use that today. And that's really what we're interested in this course, is finding the derivative functions of other functions. So again, so far we've been interested in the derivative at a specific point. Okay, today we're going to look at it in terms of a function. So really how to find the instantaneous rate of change at any point along a curve, right? So we should have a function that will allow us to find the instantaneous rate of change anywhere for the function, rather than having to find the instantaneous rate of change over and over and over and over again for the same function, right? So in the last lesson, the last section, we were looking at a ball being thrown, and we looked at the instantaneous rate of change at time equals 2 and time equals t equals 5, right? 2 seconds and 5 seconds after ball was thrown. It would have been a lot nicer if we just had a general function that we could have plugged 2 and 5 into in order to figure out those values, rather than doing that limit over and over and over again. Okay, and so that's kind of what we're doing now, is we're going to look at how to find a function that will find our instantaneous rate of change anywhere, or the slope of the tangent line anywhere for our function. Okay, so the derivative function f prime of x, right? So now I'm not looking at a point. Before I had f prime of a. Now we're doing f prime of x. This is a function. It's the difference quotient for your function. So you're going to be plugging in x plus h into your function and subtract from that your regular function divided by h and take the limit as h goes to 0. Okay. So again, here we're going to get out a function. Before we're getting out a value. The value we got out was the instantaneous rate of change, the slope of the tangent line, etc. Now we're going to get a function that will give that for any point along our curve. Okay, so example, find the slope of the tangent line to f of x equals x squared minus 2x plus 3 at the point x equals 2. So this is just kind of a reminder of what we've been doing so far. So I'm going to take this is my value of a, the point that I was interested in, and I'm going to plug that in to my point, right? So the derivative at a point was this formula, very, very similar, but here we're looking at plugging in a single value. So I'm going to have 2 plus h minus f of 2 over h. I'm going to plug these things into my equation, and it's going to look like this, right? So I have my 2 plus h in my polynomial minus 2 being plugged into my polynomial over 4. So this will be a perfect square. I'll distribute this negative 2. These 3's will end up canceling out. I'll find out what these values are, distribute this negative, etc., etc. Okay. So here I have the same line repeated twice, so I'll make sure to take this out of the book, but it's not doing us any harm here in the video, so I'm going to leave it. But in the course reader, this will be omitted, and we'll go straight to here, to us now expanding, distributing, and the same thing here, simplifying this thing down, right? I have 4 minus 4, so that's 0, plus 3 is left over. This negative distributes, so it's a negative 3 being left here. And then here I have my perfect square inside of my bigger polynomial. Okay, so finish simplifying this down. This 4 and this negative 4 is going to cancel. This 4h and this negative 2h will combine to be just 2h, and this 3 and this 3 cancel out. So I should end up with h squared plus 2h over h as the limit of h goes to 0. Okay, cancel all of my h's, and I'm left with h plus 2. Take the limit as h goes to 0, and we get out just 2. So that means that the derivative at 2 is 2. The instantaneous rate of change is 2, or the slope of the tangent line to this function at 2 is the slope of 2. Okay. Now, if I want to do this as a function and not just looking at it at a point, okay, I use my entire function, right? So f prime of x is the limit as h goes to 0 of me plugging in x plus h into my function, subtracting my function, dividing that whole thing by h. So when I do that, it looks like this. So if you notice, I'm not plugging in 2 plus h or plugging in 2. I'm using the function, and I'm using x plus h for the first portion of it everywhere x was. So we're going to do the same thing. We're going to expand this. I'm going to distribute this -2. We already know the 3's will end up canceling. I'm going to distribute this negative sign as well. Okay. So first, I'm just going to expand this term. I distribute this -2. We're just going to continue to slowly combine like terms, right? So if you notice, this is an x squared. This is a minus x squared. The x squares are gone, right? This 3 and this 3 cancel as well. This minus 2x, this negative and negative gives me a positive 2x, so those 2x's cancel. Here I have a 2hx that does not combine with anything. There's no other 2hx's. I have my h squared and then my -2h, which is coming from here. Okay, so we simplify this down. This is the term that we should get. Lo and behold, again, we have an h everywhere, so let's cancel out that common h term, and this is what we get. Okay, we have our 2x left over here, a single h, and a -2. This is continuous at 0, so I plug in 0, and I end up with 2x minus 2, which means that my function, my derivative function for this polynomial, x squared plus 2x plus 3, is the line 2x minus 2. This is not the tangent line, okay? It's just a coincidence. It's not a coincidence, but we did get a line when we took the derivative of that quadratic. This line is not the tangent line. However, this line will tell me what the slope is of the tangent line at any point on this quadratic. Okay, so I want to be very, very clear that that's what's happening. Okay, so this function allows us to calculate the slope of the tangent line at any point on our original quadratic function. So f prime of 2. So if I plug in 2 into my derivative function, I get 2 times 2 minus 2, which is 2. So that agrees, right? So when I found f prime of 2 before, I found that the slope of the tangent line at 2 was 2. Here, now that I have a function, I can find the slope of the tangent line at any point on my function. So let's go ahead and compare. I plugged in 2, and I got out 2 as well. Okay, and that agrees with my earlier calculation. Okay, so when the tangent line has a positive slope, right, that means that our function has a positive rate of change at that moment. Okay, so that means that our function is increasing at that moment, right? Positive rate of change means I'm increasing. So my function is positive whenever my derivative has a positive value. Okay, if the tangent line has a negative slope, if the tangent line is negative, right, the slope of the tangent line is negative, then that means that my function is decreasing in value as I move forward. Okay, so what that means is that the tangent line, the value of the tangent line, the sign, it's important to us because it tells us what a function is doing. If the slope of the tangent line is positive, I am increasing. If the slope of the tangent line is very large, that means I'm increasing very quickly, right, for my function. If the slope of the tangent line is negative, that means that my function is decreasing at that point. And if it's really, really large and negative, I'm decreasing a lot. Okay. So if the derivative function is larger than 0, then my function is increasing. If my derivative function is negative, then my function is decreasing. So if we look at our last example here, the x squared minus 2x plus 3, that was our original function. We can figure out what are my intervals of increase and decrease. I can figure out when my function, my quadratic, is increasing in value, and I can figure out when it's decreasing in value if I look at its derivative, right? So we can either look at a graph and just say, oh, I'm decreasing here and I'm increasing there, or we can look at it through the derivative, and we can analyze it using calculus, which is the purpose of this course, right? So here I have 2x minus 2. If I set it equal to 0, that'll tell me when the line changes from going and being negative to being positive, right? So if I solve this for 0, that's whenever x equals 1. That means that if I look on one side, my function is going to be negative whenever I'm less than 1, right? So if I come in here, let's say I plugged in negative 5, I'm going to get a negative minus a negative, I'll be negative, right? So if I plug in a very large negative value, I'm negative, which means that when I'm less than 1, my derivative is negative. So my function is always going to be decreasing when it's less than 1. So over this interval, my function is decreasing. And on the other side of the interval, my function will be increasing. Okay, so the derivative is negative when I'm in between negative infinity and 1, which means my function is decreasing then. My derivative is positive when I'm between 1 and infinity, so that's when my function is increasing. Okay, so here, this is my graph. This is the point 1. Okay, this is what happens when I plug in 1 into my function. Notice that my function is decreasing in value until I hit 1. And it's increasing in value after 1. Right? My derivative was 2x minus 2. Remember, this function is not the tangent line equation. It's the slope of the tangent line at any point on my function. So, when this function is negative, which is in between negative infinity and 1, my function will be decreasing, which is true. Okay, so here's my derivative function. This is the line. All I did was graph the line, right? This is when my graph it. This is when the derivative is 0. This is when the derivative is negative, right? Even though the derivative itself is a positive line that has nothing to do with my function here. It does, but not right now. It doesn't. Okay, this is my derivative function, this f prime of x. When it is negative, my function is decreasing. When this function is positive, the derivative line is positive, my function is increasing. At the point when my line is 0, when my derivative is 0, my function is not increasing or decreasing at all, right? It's at a minimum value actually, which is also very important in this class. So again, notice that when my derivative is positive, over here, my function is decreasing. So at 1, my function becomes positive. At 1, my function starts to increase. When my derivative is negative, okay, here's when my derivative is negative. Over this same interval of x, that is when my function is decreasing. Okay. And when my derivative is 0 at 1, that is when my function has a minimum value. So it's not always a minimum. Sometimes it could be a maximum. Sometimes it could be neither. So we talk about that later on in this course. Okay. There's many ways to notate the derivative of a function, but before we go on, let's work on this a little bit more. Let's go into Desmos and play around with a couple of other functions so that we can see the relationships between a graph and their derivatives. Okay, so we're back here. We're using the same graph that I had before when I showed you guys the secant line, except now I'm showing you guys more of the work that's going on. So this is when we were using the secant line approaching the same point to become the tangent line, right? And so we showed this in a 3.1, I believe, and we're looking at how a plus h is moving towards a, right? So the distance is getting smaller. So this is how we came up with the idea for the derivative, okay, at a point. So if I'm looking at the derivative function, okay, oops. The derivative function, so this is not the function, but what the derivative function allows me to do is look at any point along this curve and find the slope of the tangent line. So this should probably be relabeled as the tangent line at any point on curve. Okay, if that helps us to understand what's going on. So the only reason I'm able to find this is by using the derivative function. So this is my derivative. So let's take off some of these other things. Oops. Okay. Actually, we'll use both. Okay. So this is my secant line. Okay. What I need is my tangent. So let's turn off this. Okay. So here we have my derivative at any point. Okay. This green line right here is f prime. This is the derivative of my function. So notice that my function is 0 at the minimum because it's a nice graph. And what's happening here is that when my tangent line, the green line, is negative, watch what happens to this tangent. Okay, it goes this way, and then as here, the line is 0. Okay, there's no slope. And then when I'm looking past that point of no slope, this becomes a negative function, right? So it's negative on whenever my tangent line, sorry, my tangent function, okay, the green is my tangent function, f prime of x. When this function is negative, the slope of the tangent line is negative, okay? Here the slope is 0 because the equation of my tangent function is 0 at this point. And then as I begin to move in the positive direction, where my tangent function, my derivative function is positive, that means the slope of the tangent line is positive as well, right? So where my derivative function, the green function, is positive, then I have a positive slope for the tangent line. Okay, so let's wash all of this and let's start brand new. Let's use a different function. Okay, and then let's plot the derivative to that function. So notice that my derivative here is a quadratic. So let's analyze my function first and let's look what's happening. So my function g is increasing in value up until this point, up until -1. Okay, and then I'm decreasing in value until 1, and then I am increasing in value again. So that means that my derivative function should be positive up until this point right here. Okay, so let's put a marker here, -1, 0. My function, my derivative function should be positive in value until here, and it should be negative in value from this point up until this point. Okay, up until 1. Oops. And let's put this in red also. Okay, so from on this interval of existence here, so when y equals 0 for x less than -1, so for this interval of existence right here, okay, my function should be positive because my function here is increasing. My regular function is always increasing, which means that the derivative function should be positive here. It should also be positive, I don't know if I could do 2 intervals or not, when I'm larger than 1. X larger than 1. Okay, so these are when my derivative function should be positive, because this is when I stop increasing in value for my function and changing directions and going negative, and then this is when I start going positive again, when I'm increasing in value. So the derivative should be positive on this interval, on this interval, on the entire red interval, and it should be negative over this blank interval. Okay, the derivative is positive forever. From here, my derivative, this black function, is positive starting from here forward, and in between those 2 points is the entire time when my function is negative, right? So this is when it is negative, right? It's negative over this interval. Okay. And this is when it's positive. It's positive over this black shaded area, which is true once I put the function back. Okay. So my derivative will tell me intervals of increase and decrease. It'll also tell me when I'm at 0. Okay. So that's one example of a derivative function. If you lay that on top of your other function, right, notice that this x equals -1. Put these in dashed lines. Okay, they have points in common. So the top of the blue line is when the black line is 0. Right, it's when they change signs. I can take multiple derivatives as well, and it's really just me taking the derivative of the derivative. Let's go green. Okay, so if I'm looking at the derivative of this quadratic, well, I'm negative. The black line is decreasing all the way to this point, so that's when the green line is negative. It's always negative here because the black line is decreasing. So we can talk about the rate of change of my rate of change, which again is something that we do in this course as well. Okay, and so that's for a nice quadratic. I can look at my derivative for things like e to the x. Okay, so my derivative for e to the x is actually the same function. One is 3x, for instance. So if you notice, this is when the blue line is my function, g. The black line is the derivative. I'm decreasing here, and the whole time I'm decreasing, that's when the black line is negative. Once the black line turns positive, once the derivative is positive in value, my blue line starts to go back up, right? We can use x squared over so there's a little bit more going on. I'm decreasing in value, which means my derivative should be negative up to this point, and then I'm increasing, so my derivative should start to be positive, and then I start to decrease again, so my derivative should be negative. So my derivative changes signs 1, 2 different times, right? Negative time, positive time, negative time. Okay, so as I stated before in a previous video, there's many notations. We've been sticking with this prime notation, the little accent mark over the F. As I stated before, there's 2 different mathematicians that came up with calculus independently at the same time. Gottfried Leibniz was in Germany when he discovered and published a book on calculus, and Isaac Newton was in England when he discovered and published a book on calculus as well. They're completely separate entities, you know, doing the same thing. So there's different notations. Newton liked the CERN notation. It's actually the notation that's used in physics and engineering. And Leibniz had another notation which we'll go back and forth with in this textbook, or this course reader, I should say, a little bit. Most textbooks will use the Leibniz notation a lot. I really dislike the Leibniz notation. It's useful for certain times. There's certain times where it makes everything just make a much more sense. But the easiest to use while we're just doing regular calculations is the prime notation. So that's the one we're going to use most often. We'll use Leibniz when we're trying to formulate ideas and kind of talk about things. That's when we'll use the Leibniz notation. And then I'll refer back to how to use it in the prime notation. So we'll go back and forth. So those are the 2 main notations that we use. This one that we've been using so far. And this is the Leibniz notation. It's d over dx, and then in parentheses, you put your function. Okay, this is the Leibniz notation. This is also the Leibniz notation. It's just a variation of this second one, but it's the same thing. And then we have y prime, because we know f of x equals y are the same thing. So a lot of times we'll say, like, we'll have y equals mx plus b, so then we'll find y prime, for instance, right? Because that's the name of our function. So The f prime and y prime kind of go together, and then the other three that you see here are different variations of the Leibniz notation. This is an operator notation. This is generally used in higher level mathematics. You will see this in Calculus 3 when we talk about directional derivatives. But this is an operator notation. It's saying I'm using this operation on my function rather than this notation kind of says do this to your function. Okay. This is also a variation of the operator notation. So these you'll see in higher level math, right? Those of you going to Calculus 3 and above, you'll see this at some point. The rest of you get familiar with these first 5. They're really kind of the same thing. It's 2 variations of the same things. So let's go over another definition. Okay. So a function f is differentiable at a if the derivative of f at a exists, right? So that it's like, well, yeah, it should be differentiable if it exists there, right? So remember that the derivative is a limit, right? The way that we formulated this idea, even now, right? Even the way I'm asking you to calculate these at this point is to find a limit. So if the limit doesn't exist, then the derivative doesn't exist, okay? So I'm differentiable over an open interval from a to b if I'm differentiable at every point inside of that interval. So we can talk about being differentiable at a point and differentiable over an interval, right? So another theorem is that if f of x is differentiable at a point a, then f of x is continuous at a, right? So in order to be differentiable, a limit has to exist. And in order for that limit to exist, the left and right limits have to agree. And that generally means that I have to be continuous at that point as well. So now anytime we're not continuous, we're not differentiable at that point, okay? So it's possible to be continuous as well and not differentiable. So there's really 3 different kind of things that we run into that keep us from being differentiable. And so we'll talk about those right now, okay? One is that my function creates a corner. So I can be continuous, but I'm creating a sharp corner. And so when I say sharp corner, I mean something like this. So if you have, let's say, absolute value, where you have what we would perceive as a sharp corner, that's not what we would consider as a corner here, okay? Here, it's a little bit different because we curve up to a point and curve out of a point. So this would be a point where we're not differentiable, okay? So just think about what would the tangent line at this point look like? How would we draw a tangent line here, right? We really can't. So when we have a corner like this, we're not differentiable, okay? If we're discontinuous, right? So as we just said, we need to have continuity. So I cannot find the derivative of this function at this point. I can find the derivative up to and leading up to this point and after this point. So on intervals where I disregard this point, but I cannot find it here because, one, the left and right limits don't exist. Remember, a derivative is a limit, okay? And for a limit, I have to be continuous and some other properties as well, right? Next is a vertical tangent, which is kind of like having a corner, which is here, right? I can draw a tangent line, which I can't do for number 1, but my tangent is a vertical line. What is the rate of change of a vertical line? It's undefined, right? I'm 0 on the bottom because there's no left or right movement. So the instantaneous rate of change does not exist here. There's no actual defined slope, okay? So let's do, I think, one more example for this section, and then we'll begin chapter 4. So here we'll just kind of use the derivative and talk about what it means in an application setting. So here we'll talk about money, right? So the dollar amount C to produce Q quarts of ice cream is given by a function C equals f of Q. So you plug in the number of quarts to a function and the output will tell you how much it cost, right? So we want to give the units of each number in the expression and write what the expression means in words. So I'm going to give you some input and outputs and we write what that means. So here, this is a function, right? My cost function. If I'm plugging in 4, that means I have 4 quarts of ice cream. If I'm getting out 10, well, that means that it costs $10 to make 4 quarts. Okay, or to rephrase it, 4 quarts of ice cream cost $10 to produce, right? That's my production and cost function. Here, f prime of 2 equals 1. So now I'm talking about the rate of change. Well, rate of change is the change in the amount of dollars divided by the change in the number of quarts. So if I am interested in what's happening when I produce 2 quarts of ice cream, it means my rate of change is 1, right? It means that at this instant, at 2 quarts of ice cream, my price is increasing by $1 to produce 2 quarts, right? So when we're producing 2 quarts of ice cream, the price is increasing at a rate of $1 per quart. F inverse of 12 equals 3. Remember, inverse means that I'm plugging in cost, and then what I'm getting out is quarts. So the inverse function is basically telling me that when it costs $12 to produce ice cream is when I am making 3 quarts, right? Costs $12 to produce 3 quarts of ice cream. Here I'm doing the same thing, but I'm talking about the rate of change from my inverse function. So f inverse prime of 15 over 5. So this is still money, and this is still quarts, but now it's in terms of rate of change, right? So the amount of ice cream that I'm producing at when it costs exactly $15 is increasing by 5 quarts per dollar. Okay, so when it costs $15 to produce ice cream, the rate of production is increasing at 5 quarts per dollar. So we talked about this when I was playing with Desmos just a second ago, that we can do more than just the first derivative. I can take the second derivative, third, fourth, fifth. Some functions I can take the derivative of infinitely, right? Meaning that there's no limit to how many derivatives I can find. I can always find the rate of change of the rate of change of the rate of change of the, etc., right? Some functions you can only find the derivative once. Some functions you can only find the derivative twice. And we do explore that a little bit in this course. So when we have to take more than one derivative at a time, we call those higher order derivatives. Okay, so if I take the derivative of a derivative, then that's a second order derivative because I had to take the derivative twice. We would write that as f double prime, or in the Leibniz notation, the d gets squared and your input variable gets squared. Okay, so we can take multiple derivatives of a function. When we're talking about position, it goes position is our regular function, velocity is our first derivative, acceleration is our second derivative, and then we get into third, fourth, and fifth, which is jerk, and then snap, crackle, and pop, actually, is what they're called. We'll talk about those a little bit later as well. But we can take multiple high-level derivatives. We just would do this process over a second time or a third time or a fourth time.